juniors now. We can use the big words.
We come down the way.
Go to, and, let's review metallic bonds and make sure we understand. Remember, metallic bonds are completely different than ionic, but all bonds, no matter what kind they are, always come down to positive, negative attraction. So, if ionic bonds are metals and non-metal combination, metals are metals to metal combination. And so what happens is you're involving all cations for metals. So these are all atoms that are going to give up electrons. Where do they give it up to? To the electron C. And so hopefully I clarified the difference between electron C and an electron cloud. Did I do that all right for you, Maria? She's staring into space, thinking about Saturday and Sunday, what she's going to be doing.
No.
Okay,
Yeah.
so you understand that the electron C is interspersed in between the electron clouds. It's that area around the atoms in the electron cloud. So they give up these electrons to electron C, so these cations become positively charged, and they're attracted to this negative electron C. That's the bond. By the way, metallic bonds usually, for the most part, are weaker than ionic bonds. They're weaker. Okay. So these electrons that are given up to electron C do not really belong to the original atom. In fact, they belong to all the atoms together. And so they have no specific location anymore. So they are called delocalized electrons. All right, so we also established the fact that the more electrons that are donated to electron C, the stronger the metallic bond's going to be. So if you have alkali metals, they donate only one per atom. And so you have these positive one charges for the cations attracted to the negative electron C, which is not as strong. Not a very strong metallic bond, but if you try alkaline earth metals, they donate 2 electrons to electron C. Now you have a two positive charged cation attracted to this more denser electron C, more negative electron C. That's a stronger bond. So the more electrons, the stronger the bond. Iron typically donates 3 electrons to electron C. Pretty strong. All right, so that is a good diagram, as we said. You can see the electron C is a lot denser for the alkaline earth metals than they are for the alkaline metals, because they're donating 2. So the density, the electron C density is greater for alkaline earth metals than they are for alkaline metals. So alkaline earth metals have stronger metallic bonds than alkaline metals. Okay, now let's go back. Now that we know what metallic bonds are, we can go back to those properties we talked about. Ductility, malleability, luster, conductive, and now we can explain those in terms of metallic bonds. So let's look at malleability, the ability to be pounded into shapes. Why is that? Well, the metal cations are able to slide along each other and reform bonds. So if you pound a metal, the cations just shift around, or shift in that electron C, and once you stop pounding them, what happens is the bond can be reestablished real easily. It's still surrounded by the electron C, so these cations can shift. That explains malleability. That's why metals are malleable. They're very easily shifted, and the bond reestablished. Ductility, ability to be stretched into wire. What you basically do when you stretch metal is you're causing layers to slide along each other as it elongates. Why can they slide? Because these cations, again, can shift positions. They're still surrounded by the electron C, but they can shift. These cations can shift around, and as they shift and you stop stretching it, what happens is the electron C is still there, the cations are still there. They'll reestablish the bond. So these cations shift, both in malleability and ductility. What about conduction? Well, that's the easiest. What exactly is a metallic bond? It's electrons in the electron C that are free to move. What is electricity? It is a form of energy but it's basically caused by the free motion of electrons. Electrons are moving through that copper wire that is powering the devices in your home and the lights in this classroom. It's movement of electrons. Well, does a metallic bond have easily moving electrons? Yeah, delocalized electrons, they're free to move. Perfect situation for conduction of electricity. Now, some metals conduct better than others. You know, what do we use for conduction within your homes? We use copper. Copper is an excellent conductor of electricity. Those delocalized electrons are free to move probably easier than most metals. Does anyone know what metal is even better than copper in conduction of electricity? Turns out silver is a better conductor. But you're not going to have silver wires in your home. It doesn't make sense. Economically, no one could afford a house wired by silver wire. What's that? Unless Isaac somehow gets on Jeopardy and wins the $1 million. And so he's gonna put all his winnings into putting silver wire into his household.
Nothing else.
I can see you doing that, actually. Okay.
So what do you spend it on? Well, you see, there's a wire.
Yeah, exactly right. And so what happens, he goes on vacation, some thief finds out, and comes home and all the wires pulled out of the walls in his house. They're doing that with copper, you know that, don't you?
Wait, what?
Thieves actually go into houses and rip copper wire out of the house. They actually do, they especially do that, unscrupulous people will go into houses that are under construction and pull out all the wiring because it's copper. And then you can get, when you take it to recycling, you can get good, for scrap copper, you can get a lot of money. People actually do that. What a sad testimony.
That is.
Yeah. Lustrous, what's about that? Well, the delocalized electrons, again, have a great interaction with light and reflect those wavelengths of light. What is actually, so basically in luster, when you have metals that reflect light of various wavelengths, what's it reflecting off of is the delocalized electrons. That's what's happening. If it wasn't for the delocalized electrons, metals would not have a sheen to them or a luster to them. So again, what would be your responsibility in regard to these properties is you would have to explain to me, if I give you a property of a metal, why does that property exist? And you must explain it in terms of the metallic bond. Okay? Yes.
What about like matte metals?
What about it?
Like, they don't have really much of a luster.
Well, matte metals all the time, many times, there's two situations with that. It's either they're combined with other elements, again, like we talked, become some kind of metal combination or metal to non-metal combination, or they put a sheen or covering or some kind of glaze over the metal to cause it not to be that way. Okay. And the last thing is, we've already mentioned this, but we need to put it in writing. As the number of delocalized electrons increase, so does the hardness and the strength of the metal. As I said, if you went to college and got a degree in metallurgy, you could probably write your own ticket. They're in great demand. Metallurgists are in great demand. They're doing not only working with metals and combinations of metals, but they're also working with harnessing new types of metals and new structures. Metallurgy also goes into carbon compounds and things like that. And we know that graphite is huge in certain things, like in golf clubs and things like that. So the research is huge. And then really one of the main goals is to come up with something with a tensile strength stronger, much stronger than steel, but 1/10 the mass. Can you imagine if you were able to come up with something that was 10 times stronger than steel, and yet was 1/10 the mass of steel? You would have something, wouldn't you? Think of the things you could do with it. You know, the weight of steel is pretty heavy, and what do? We build buildings out of it, right? And one of the limitations of building buildings with a skeleton structure, girdle structure to a building is the weight factor. What can that building handle as far as weight? What if you could build that same building with materials that are 1/10 the mass, but 10 times the strength? What would be your limitation? You could build buildings half a mile high, which a lot of architects are even putting on the drawing books. All we need is the right material.
That'd be so scary to work up there.
Another thing, but another thing they're working with is the tensile strength of the fiber that would be so strong that you could actually have the fiber connected and anchored to the earth and go out to orbit, to an orbital station. And so what would happen is you'd have an elevator attached to that cable, and that cable would just keep taut all the way as the earth even spins on its axis. Take an elevator on that cable all the way out to the space station.
Just sounds like
There's actually plans on the book for that. Now, what does it take? It takes a special material that could withstand that kind of tensile strength.
That's terrifying.
Yeah.
I don't know, I think it'd be, if it was safe, it'd be fascinating. Anybody could go into space then.
I don't even trust hotel elevators.
These companies that are right now, even at NASA, Kennedy Space Center, that are going to, within a year or two, going to give rides to people into space. An average person. It's gonna happen. It's gonna happen before you guys graduate from college. You're gonna have rides into space.
raise up our
That would be
profile.
really cool to like go into space, but it would also be terrifying because like what if something went wrong?
Imagine how
Yeah,
Why?
it's not like we've never had anything go wrong.
Yeah.
Yeah, I understand what you're saying. But obviously, it's going to be a situation where this won't take place unless it is a lot safer than, our history with the shuttle, for instance. We lost 2 in the fleet because of things. Anyway,
Imagine how long that elevator ride would be.
it depends how fast. That if you can rise up from that cable at, let's say you can rise up at 50 to 100 miles an hour, it would take, to go into space, you would be 50 miles probably, around 20 to 50 miles. So it'd take half an hour to get up there.
That feels so weird. Would you like sit down in the elevator probably? Have like a strap on?
I don't know, probably at first because, I don't know, I would imagine the acceleration would not be
Immediate.
dramatic like a rocket speed, but you would not be pulling like 8 G's of force. They would start off accelerate at a low rate, but by the time it reached speed, you wouldn't know it. So yeah, you could be standing around, walking around as you're going up at 100 miles an hour. Yeah.
Yeah, I know, that's what I'm thinking. What if like something goes wrong with it and
Well, that's the thing, they're not gonna
You
do
fly
this
off.
with the idea, well, maybe something go wrong, maybe something will go wrong, we don't know. I'm sure, like I said, what does it depend on? Depends on the strength of the tensile strength of the materials they're gonna be using. So, and a lot of it, what they're thinking of is carbon networked fiber is what it is. Now, we have materials here on Earth that are not metallic, that are stronger than steel. And they're working diligently on it, and that's spider web. Spider webs are incredible. Now, I'm not saying that spider web go all the way around space, but what if they could perfect how spiders weave that material and make